Understanding physics, units. In this video I'm going to talk about units. We'll start with a question: how long is a piece of string? And you might answer it's 1.6 meters long, or 6 feet long, or 1.2 cubits, 220 barleycorns, 0.9 lactas, whatever that is. Basically, you can see that scientists around the country, around the world, need to be using the same units of measurement. Otherwise, we're going to get very, very confused. So we need some kind of an international system of units that all scientists can use, and then they can share data and communicate with each other. Okay, and we use an international system, Système International, the SI system. And in the SI system, which kind of came from the metric system, which I believe started in France, we have base units. There are 7 base units. In mechanics, the important ones are mass, length and time. The unit of mass is the kilogram, not the gram, the kilogram. The unit of length is the meter. The unit of time is the second. There are some other base units as well. The ampere is a base unit. The Kelvin, we'll talk a lot about that when we do thermal physics. And amount of substance, the mole, is a base unit. And then there's another one which I don't think I've ever used, is the candela. Mass, length and time in mechanics, they are the important ones. And the kilogram, the meter and the second, they are our base units. All other units can be derived from these base units. How big is a kilogram? Well, it used to be the mass of a litre of water. Now somehow it's defined in terms of Planck's constant. Look it up if you're interested. The meter, there's been all kinds of definitions of a meter to do with pendulums and things, and one definition was it's the fraction of the distance from the North Pole to the equator on the meridian that goes through Paris. So I believe from the North Pole to the equator on a line that goes through Paris is a certain number of meters. Now it's defined in terms of the speed of light, and the speed of light is now a universal constant. The second used to be a fraction of a day being the time between the average time between noon and noon. Now it's defined in terms of some radiation that a particular isotope of cesium emits. So there are definitions. We know how much a kilogram is and a meter is. We know how much a second is. Now, derived units, apparently there's about 22 important derived units, and then there's a few other more obscure ones. Let's consider the Newton. The Newton. Now, how much is a Newton? Well, force is measured in newtons, and it's the force required to give a mass of 1 kilogram and acceleration of 1 meter per second squared. If you have a mass of 1 kilogram and you apply a force to it, a resultant force of 1 newton, then its acceleration is 1 meter per second squared. In other words, a newton is a kilogram meter per second squared. If you think about F equals ma, that should help. F newtons, m kilograms, acceleration meters per second squared. Okay, remember F equals ma, and you can figure out what the base units of the equivalent base units of the Newton are. Here's lots of other derived units and their equivalent base units. We've said a force is, a Newton is kilogram meter per second squared. If you think about F equals ma, you can get that. Energy is in joules. Think work is force times distance. Power is in watts. Think power is energy over time. Then we have coulombs. A coulomb is an amp second. Remember that an amp is a base unit. A volt is a joule per coulomb. See, it's getting a little bit complicated now. An ohm is a volt per amp. Just really worried about the mechanical ones for the moment, boiling things down to kilograms, meters and seconds. This is a very, very, very typical exam question. Let's have a go at them now. Here's a list of combinations of base units. Which combination gives us momentum? I'll tell you what, you have a go at it yourself. Pause the video and I'll show you the answers in 2 seconds. Okay, so momentum, kilogram meters per second. Momentum is mass times velocity, so kilograms times meters per second. The next one is a little bit trickier, Pascal. Well, a Pascal is a Newton per meter squared, force divided by area. So looking at my scribbled working out, this is how I would work it out. We've got pressure is force over area, or stress is force over area. So MA divided by area, so kilogram meters per second squared divided by meters squared gives us kilograms per meter second squared, which is answer D.